Hello everyone, welcome back. This is part 4 of our acid and base chapter. And in this chapter, in this part I should say, we're going to calculate the H3O plus for a weak acid using the Ka value. We're going to calculate pH for a weak acid when approximation doesn't work. And remember, when approximation doesn't work, we're going to have to use the quadratic formula. And then finding equilibrium constant when you know the pH. And so we're going to use our knowledge of how we know that the pH and the H3O plus concentration interact with each other to be able to find that in a reaction. So there are two sources of H3O plus. The H3O plus from the weak acid and then the H3O plus from the autoionization. The weak acid mixture is complicated because it only partially ionizes. So we don't know from the initial concentration of the acid what the ending hydronium ion concentration is. So since we don't know what the changes are in a lot of these, we're going to have to use the ICE formula to find out what the H3O plus concentration is at equilibrium, and then that will also allow us to then calculate the pH of that. So the Kas I've got here, we saw this earlier, of your weak acids. You've got Kas and you've got pKas, and remember that your weak acids are not going to ionize completely, and so you're going to be left with some of the original acid in the mixture. So if we're finding the H3O plus of a weak acid, we're going to have to use our ICE table. And so I've got it kind of miniature up here so I can have plenty of room to work these problems. So in our ICE table, we have HCN aqueous going to H3O plus and CN minus. It tells us in our problem that the H3O plus of the solution, what we're finding is H3O plus of the solution, and we have a 0.1 molar HCN. All right, so that tells us that we have 0.1 molar HCN to start with. At the beginning of the reaction, you remember from equilibrium that we have nothing of the products yet because we haven't started yet. And so we have 0.1 and then 0 and then 0. Now, since we don't know what the change is because we don't have any other information, we're going to have to use X's. And in a weak acid, we know that we're going from the weak acid to partial ionization of H3O plus and CN minus. So that means that we're going to use up X of HCN, and we're going to make X of the H3O plus and the CN. How do I know that? Because when I look at the balanced chemical equation, they're all 1 to 1 to 1. So that told me that it was going to go down X and up X for this. And so at equilibrium, I'm going to have 0.1 minus X, and then X, and then X. All right, so all of that should be familiar because that's what we did with equilibrium. All right, so first step, I'm going to look at the Ka. All right. The Ka, and like if it's not on these problems, you're going to have to look them up, okay? So you look them up in a chart or whatever. The Ka for this, when I'm working the problem, I'll tell you what it is 4.9 times 10 to the minus 10. That's extremely small, okay? Extremely small, and so that means that I can probably use the approximation rule for that because it's way smaller than 10 to the minus 5. So that's going to help me mathematically, but I'm going to go ahead and just set it up how it would be. The H3O plus times the CN minus. Nothing is squared or anything because it's they're all 1 to 1. Okay, and so that's the same as X times X divided by 0.1 minus X, okay, because H3O plus is X, CN minus is X at equilibrium, and then HCN is 0.1 minus X. All right, and so that's the same thing as, and since I can use the approximation rule, that means that I don't have to worry about that minus x, so that's going to be x squared over 0.1. Okay, and so I can then solve. That's going to be equal to 4.9 times 10 to the minus 10, because that's Ka. And so that means, so in step 2, what I'm going to do is I'm going to cross multiply, and I'm going to say that x squared is equal to 0.1 times 4.9 times 10 to the minus 10. Okay, and that's equal to x squared. And so if I take the square root of x squared is equal to the square root of 0.1 times 4.9 times 10 to the minus 10, and I'm writing all of these steps so you can follow me easier. Then x is going to be equal to 7 times 10 to the minus 6. Since x is what we are at equilibrium should equal the H3O plus concentration, that's what x tells me. It's also the cyanide, but the H3O plus is really what we're interested in, especially because then once I have that, I can go in and take the negative log of it, and I could tell you what pH was if I needed to. Make sense? These are very, very similar to our equilibrium problems, because now we're doing acid-base equilibrium. And then you have one, remember, an HF, remember, is a weak acid, so you're going to be doing that the same way. All right, so sometimes, as we saw in equilibrium, we don't always have the, it's not always low enough to use approximation. And the example here I'm going to give you for this HClO2, the Ka, is 1.1 times 10 to the minus 2. Okay, and that's a pretty large one, so my approximation rule is not going to work on this one, so I'm probably going to have to do the quadratic. Okay, and I've already done, again, you're going to see as we go through these that especially when they're 1 to 1 to 1, you know, you're going to know that at equilibrium you're going to be 0.1 minus x and then plus x plus x. All right, so that's so I went ahead and did that one for you. If it's not 1 to 1 to 1, that's going to be different. So don't forget to always check that. So that's our ice table. So once I have my ice table set up, I know, again, H3O plus, so I'm doing the products, divided by the reactants, which is always going to be your acid in acid reactions. And remember, so far all we're doing is putting these in water. I haven't reacted them with a base or anything. All I've done is I've been putting them in water to see what happens when they're in regular water, okay? And so the Ka is 1.1 times 10 to the minus 2. So you got to have the Ka to work these. All right. So again, this is going to be 1.1 times 10 to the minus 2, and each of these was x, so they're going to be equal to x squared divided by 0.1 minus x. Now, since this one is a big number, I can't use approximation, so it's going to, that minus x is going to stay there. So when I cross multiply this time, okay, I'm going to not only multiply the 0.1, but I'm also going to have to multiply the x by that. So what I end up getting is 1.1 times 10 to the minus 2 times 0.1 minus, because that's a minus x, right, minus 1.1 times 10 to the minus 2x. And that still equals x squared. Okay, so if I was able to get rid of that x, I wouldn't have had to worry about the other part of that. So then what I want to do is I want to put any like terms I have together. So I've got to multiply these two numbers together, which is going to be 1.1 times 10 to the minus 3. Okay, that's those two numbers. And then I've still got my minus 1.1 times 10 to the minus 2x, and that equals x squared. All right, so you remember, since I'm going to be doing the quadratic, that I'm going to rearrange that so that it's in the form of the quadratic, so of the line. So x squared plus 0.011 minus, is that right? Is it 00 minus 00? Okay, minus 0.0011. Okay, so that's my x. Oops, that's why it looked funny to me. All right, so x squared minus 0.011x minus 0.0011, and that's all equal. And so that's because I can find out a is 1, b is 0.011, and c is a negative 0.0011. So that's how I got my quadratic numbers that I'm going to use, right? And if you remember the quadratic, that x is equal to a negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So now I'm going to plug those in. So x is equal to the negative 0.011 plus or minus the square root of 0.011 squared minus 4 times 1 times a negative 0.00 0.0011. Sorry, I always seem to run out of room. I should write smaller at the beginning. All right, so negative 0.011 plus or minus the square root of 0.011 squared minus 4 times 1 times 0.0011 negative. All right, and then that's all divided by 2 times 1, 2a. All right, so when I do all that math, and again, you've got to be one with your calculator and make sure that you can get these, okay? A negative 0.011 plus or minus 0.0672 divided by 2, right? So I do one of them adding and one of them subtracting. So one of my x's comes out to 0.039, and it's a negative, or x is equal to 0.028. Now remember, when I do the quadratic, I've got to figure out which one is not real. Well, it can't be a negative number, right? Can't be a negative number. All right, so I know that one can't be it. So this is going to be my x, and so my x is the concentration of the H3O plus. So H3O plus equals 0.028 molar, and then I take the negative log of the hydronium ion concentration, and that's going to give me 1.55, okay, and that's the pH, because that's what it was asking me for. So a big part of this is, number one, not making any mistakes, especially on, you know, your where your decimal is and how many places and all that, and then the steps you have to go in order to make sure that you're covering everything. But the bottom line is, when you get done, you should have 0.028 as your x, and then take the negative log of that to get your pH. If you're not getting that with your calculator, then we need to have a one-on-one with either me or tutor or somebody else so we can walk through those steps that you take when you're doing the quadratic formula. Then you have a practice. All right, now sometimes we don't know what the Ka is for something because it could be at a certain temperature or what, it changes. And so if we are given the initial conditions, so we've got 0.1 molar weak acid solution, so that's going to be that concentration of your HA, right? It has a pH of 4.25. Find the Ka. Okay, find the Ka. So why is that 5.6 times 10 to the minus 5 written on that chart? Because the pH is going to tell me what the hydronium ion concentration is. So if I want to find that number, I'm going to have 10 to the negative pH, okay? So that means 10 to the negative 4.25. And when I put that in my calculator the correct way, at equilibrium, that's telling me it's 5.6 times 10 to the minus 5 molar. Because it said a weak acid solution has a pH of 4.25. Find Ka for the acid. So I need to be able to fill in this chart in order to figure out what Ka is. So I have 0.1 to start with. I had 0 to start with here. So that means that in the H3O plus, I gained 5.6 times 10 to the minus 5. And since the acid, the A part, the anion, is 1 to 1, that means I also gained 5.6 times 10 to the minus 5 of the anion, because they're 1 to 1 to 1. Since it's also 1 to 1 to 1 on the reactant, that means it had to go down 5.6 times 10 to the minus 5. So at equilibrium, these two are 5.6 times 10 to the minus 5. This one is 0.1 minus 5.6 times 10 to the minus 5. Y'all with me? And our times 10 to the minus 5 is very small compared to 0.1. So we can use the approximation rule, I believe, if we need to. So we can ignore that minus 5.6 whatever, right? Because it's not going to change the number. So then we just plug in Ka equals H3O plus times A minus divided by the acid. So when I plug those numbers in, I've got 5.6 times 10 to the minus 5 times 5.6 times 10 to the minus 5 divided by 0.100. And if you want to subtract the 5.6 times 10 to the minus 5, you can. But like I said, it's not going to change this number past these decimal places. So you don't even have to bother with that. And so when you put that in, your Ka should calculate out as 3.1 times 10 to the minus 8. So that one was a little easier. Okay, so when it tells you your weak acid concentration, it's telling you the initial acid, and then the pH is what's at the end. Okay, and then you just plug and play. And there's your practice. And that's the end of part 4.